If X has covariance matrix sigma, then we know that sigma is symmetric. And that its diagonal elements are variances and hence non-negative. And in fact, I'm going to write positive because we are going to eliminate constants in our random vector. So our random variables are going to have some variance. So the diagonal elements are going to be positive. 0 is not allowed. But there is one more condition that a covariance matrix has to satisfy. It's filled with all the covariances, and some of them, of course, are variances. And you know that covariances and variances have relations to each other. For example, correlation is the covariance of xy divided by the two standard deviations. And correlation has to be between -1 and 1. So you can't just have arbitrary numbers and call them covariances and variances. They have to have some relation to each other, and we are going to specify what that relation is. And we're going to do that by looking at a particular linear transformation of the x's. So recall that if you have y, a linear transformation of x, then the covariance matrix of y is gotten by taking A, multiplying by the covariance matrix of x, and then again by A transpose. Now, y is an m cross 1 vector, and so as we have written many times, the dimensions of A and B are determined by that. So we will look at the special case when m is equal to 1. In that case, this vector isn't a vector at all. It's just an ordinary random variable y. And A is just one row, which I will call A1, A2, AN. It doesn't need the other subscript because it's just has one dimension. And so sigma of y is and sigma y is just 1 cross 1. It's a number, which works out because this is 1 cross n, and then you have n cross n, and then you have n cross 1. But what number is it? It is a very well-known number. It is the variance of the random variable y. And therefore, it is non-negative. And so what we have shown is that if you take any n vector A, there were no constraints on A at all, other than it was just one row. And now I'm going to try and write A with a double line. What we have seen is that if I take A, I multiply by sigma, and then I multiply by the transpose of A, I get a non-negative number. And another way of writing that if you take the vector C to be a transpose, then this is C transpose sigma C is non-negative for all C, and this is the condition for a matrix to be positive semi-definite. A positive semi-definite matrix is a symmetric matrix that satisfies exactly this condition. And it turns out that not only does a covariance matrix have to be positive semi-definite, every positive semi-definite matrix is also a covariance matrix of some random vector. We are going to assume that our random variables are not linearly dependent on each other, and so I can state that another way. We will assume that none of the elements of X is a linear combination of the others. That is, we won't have situations where our vector x consists of x1, x2, and also x1 plus x2. If we have x1 and x2, then we don't need the additional variable x1 plus x2. We have all the information that we need in x1 and x2. Under this condition, sigma is actually positive definite. And that means that it is invertible. Now, if this linear algebra is not familiar to you, don't worry about it. Just assume that the vectors that we will be working with have covariance matrices that are invertible. And that is going to be very important when we study the multivariate norm.